I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
To everyone, so welcome to this episode number 59 of Physics Matter Colloquia series. So I'm Christine Dauf, so currently working at the European Spallation Source in Sweden, and I had the honor to be serving as chair of the Forum of International Physics at the American Physical Society, which support this series. So the Physics Matter Colloquium series connects a global audience, so every month with engaging talk, fostering capacity building in developing regions and highlighting the role of large-scale research infrastructure in advancing science and society. So currently we are focusing on Africa. So following the presentation from Professor Raja Moulsa, so a leading advocate for women in science in Morocco, Professor Thierry D'Almeida addressed the African socio-economical challenge and highlighted how the XTEX Lab, in partnership with the government in Benin, is tackling them. So then we have, last month, Dr. Joyful, who from South Africa promoted astronomy as a tool for development across all nations. So now, in the coming months as well, we will be further exploring the UNESCO perspective by having the presentation by Rich Michael Wellington in Ghana, so that's going to be in October, followed by a summary of the African strategy in November. And we're going to conclude the year with the International Year of Quantum Science and Technology by a presentation by Professor Anna Maria Cotto, so the chair of this International Year of Quantum 2025 Steering Committee. So this is a very rich and diverse program available on our website and all the different YouTube presentations that you can revisit later on. Today, so the different people on the panel, so I'm delighted to have with us, as a panelist, so Munia Lassina, so Dr. Lunia Massina just received last week to mention, so the 2025 UNESCO Alfosa International Prize for the promotion of young scientists in STEM. So she is also member of the Forum of International Physics, member at large. And we have with us, our dear colleague, Alan Hurd, also former chair of the Forum of International Physics and being live from Los Alamos, so in the US. But today, so this is a great honor for us to introduce Professor Paul Woafo, so Professor of Physics at the University of Yaoundé in Cameroon. So he holds both a doctorat d'état, so it's Franglish, so a doctorat d'état and a doctorat de troisième cycle in nonlinear dynamics, and he has built an impressive career combining fundamental research with applied innovation. Professor Woafo leads the modeling and simulation and engineering biometric and prototype group, so where his works cover the electromechanical system, bio-inspired device, telecommunication circuit, optical and biological oscillator, and application ranging from robotic to energy harvesting and the medical technology. So his research has resulted in more than 300 scientific papers and the supervision that he had for more than 70 PhD theses. So he's a fellow of the Cameroonian Academy of Science, of the Physical Academy, of the Physical American Physical Society, sorry, and he has been recognized internationally, so including also in the IUPAP 2020 award for his outstanding achievement as a scientist, an educator, and science leader in Africa. So please join me in welcoming Professor Woafo, and we will give you the floor now. So Professor Woafo.
Thank you very much, Christine, for the nice introduction. I hope my presentation will reflect what you have just said. Well, good day to all. I am Paul Woafo from the University of Yaoundé 1, and I will give you some information on nonlinear physics in Cameroon, and give some information on why we are interested on the studies on chaos and why inspire electronic oscillators. So the plan of the presentation is as follows. First, I will give some general information on nonlinear physics in Cameroon, starting with, for those who are not familiar with the field, starting with the definition of nonlinear physics, with focus on soliton and chaos. And then I will give some information on when the nonlinear physics was introduced in Cameroon, and give some facts on research on soliton in Cameroon, and some facts on the development of chaos research in Cameroon. And then at the first of this first part, I will give some information on my present research topics in my research group. The second part, I will talk on the omnipresence of chaos in different scientific fields. This will just explain why we are interested in doing that in Cameroon. I will not really present the results we have already obtained, because I was told that I have to give the information so that people at the graduate or undergraduate student will be able also to follow what I will explain. Then at the third part will be on the bio-inspired electronic oscillators, explain why we are interested on that, and explain the principle to design bio-inspired electronic oscillators, and give some examples. For instance, the heart pump toys and the flying burst toys. Well, as I was indicating, it was a little bit delicate for me to present. Presentation will be for those already working on nonlinear dynamics or nonlinear physics, or for general public. So you will excuse me to go really inside the heart of the field on which I'm presenting today. So as I indicated, the first part is on the introductory facts on nonlinear physics in Cameroon. Well, a nonlinear system is a system with which is in the state where the response to an input is not proportional to the input. So the output is not proportional to the input, and it is present in different scientific and technological fields. And most of those systems are described by nonlinear differential or partial differential equations or discrete equations. And when we mean nonlinear differential equation, we mean the presence of terms with power greater than 1 or some function of the unknown. And those systems are dominated by many striking and complex structures or responses, among which we can cite solitons and chaos, on which Cameroonian scientists are strongly working. Now, solitons are nonlinear waves with particular characteristics. The first one is that they are special, they have a sort of special localizations, and they propagate with a constant velocity and shape, and they conserve their identity after collision with other waves. And they are organized in two main groups. The first one is the group of topological solitons, for which the amplitude of the solitons is independent of the velocity, and they can exist as defects in the physical system. We have flux terms in Josephson-Johnson's, dislocation in crystal, domain walls in ferroelectric and ferromagnetic system, for instance. The second group is non-topological solitons, for which the amplitude depends on the velocity, and most of the time they cannot exist without being mobile. So when the velocity is equal to 0, the amplitude is also equal to 0. As one concern chaos, it is a system is said to be chaotic when it is described by deterministic equations, but for which the output or the temporal behavior is unpredictable and extremely sensitive to initial conditions. And as we are talking on nonlinear systems, the chaotic systems are nonlinear, and they are said to have at least 3-dimensionality. But we also have spatial chaos and spatial temporal chaos. I will come back to that later. And nonlinear physics, specifically chaos, is strongly impacting on research in physics and in other fields. So that some people think that nonlinear physics and chaos will have the same consequences as the quantum mechanics did at the beginning of the 20th century. Now, when chaos was introduced in Cameroon, I'm presenting here 2 photographs of Professor Kofane. The second one is where he was receiving a prestigious prize given by the African Union. And he's the one who introduced the nonlinear physics in Cameroon in 1988. After obtaining his PhD thesis in France, he arrived in Cameroon and met 3 students already engaged in PhD studies. And they were working on wood, looking for the elastic, viscoelastic, and plastic properties of wood. And by a sort of providence, Professor Kofane became the new leader of the group and decided to change the research topics of the 3 students. So the first one received as a topic the work on analyzing the discrete nature of materials of the propagation of solitons, specifically domain walls and dislocation in ferroelectric materials and in mechanical structures. And the second topic was solitons in monoatomic and diatomic lattices. And the third one was the mathematical solution of some nonlinear partial differential equation, having solitons as solutions. At the end of the supervision of the 3 theses, we worked for 3 years. I was one of the PhD students. I worked on the first topic that you have there. After 3 years, there was a sort of what was called at that time a striking consequence, because we defended our thesis, 3 of us, the same day, with about 6 articles, plus one article published in outstanding journals by the American Physical Society, by IOP, UK, SVA, Journal of the Nordic Countries Academies of Science. So that was a good starting point that some of us follow after with Professor Kofane, and I've been privileged enough with my contribution in terms of supervision of PhD thesis and publication of research articles, and also as to open new research topics. Now, the nonlinear physics groups or nonlinear dynamics research or nonlinear science research in Cameroon is by very far the most prolific research topic in our country. Today, I think we have about 1,000 articles and more than 2,000 PhD theses supervised by people coming from the initial input that was given by Professor Kofane. And most of the former PhD students are doing well, very well in different universities all around the world, starting from Cameroon in the 10 state universities, but also in the Central African Republic, in other countries in Africa, Central African Republic, Gabon, Chad, Botswana, Senegal, but also out of Africa, in USA, in Germany, in Austria. So people are working very hard in those countries. And we also have strong collaborations with many research groups all over the world. I would like to emphasize here on the strong support that we receive from the Abdul Salam International Center for Theoretical Physics, where a good number of former PhD students of this group were associate members, which gives them the opportunity to travel to stay at the center, at the ICTP for 3 months, every time that they go there, and to get information on scientific literature when they are present there, or discuss their work with other scientists when there are conferences. Now, what are the research topics on soliton in Cameroon? We are looking for the conditions to have a soliton in physical, biological, optical, electrical systems, but also how a soliton propagation is affected by internal irregularities or external excitations, and how solitons affect the properties or the functional role of a physical, biological, optical, electrical, or technological system. And the last question we are looking for is to how to generate very short size solitons. The system in which we are working are taken from condensed matter physics or solid state physics, surface science, electrical transmission lines with conducting and superconducting components, optical fibers, biological lattices, and hydrodynamics, etc. Before 1995, most of our contributions in nonlinear physics were almost directed on research on solitons. But having the opportunity to be invited to the ICTP, we were looking for nonlinear system where we could conduct experimental investigations in Cameroon, along with the theoretical investigation, because all our work on solitons were only theoretical investigations. So a shift on research chaos came in 1995. After 3 stages I received, I got at ICTP. So I was lucky enough by being invited to ICTP for conference in 1994 and 1995, and then got the ICTP associate shame. And later on, I received an equipment grant from the the Academy for the World, yes. And that is how chaos research got its impetus in Cameroon, with theoretical and experimental works. I would like to indicate that, as I said before, when we defended our thesis in 1992, it was almost, I think, the first time people were defending their thesis in Cameroon without traveling abroad. We did our thesis in Cameroon without having the opportunity to have a stay in a foreign country. We do that in Cameroon, and we did that in Cameroon, and we obtained our thesis there. And that's why I was saying that it was really a striking effect in the Cameroon scientific community, not only because of the publication we got during our thesis works. Now, many research groups are present in working on nonlinear physics in Cameroon. And presently in my research group, we are working on the theoretical and experimental studies of the dynamics and synchronization of nonlinear micro electromechanical actuators. We are looking for new actuation devices for industrial processes, for home devices such as mixers, sieves, and screens, electric energy harvesting, but also we are working on nano system where we have to take into account the quantum effects. The second main topic in our group is the theoretical and experimental study of complex dynamics of optoelectronic devices, where we are analyzing the dynamics of the semiconductor lasers when they are powered by self-contained electronic oscillators. And the objectives is to look for chaos, optical chaos cryptography. We also work on optoelectronic oscillators having nonlinear electronic component in their electric part for the generation of special optical and electric signals for telecommunications. The third main topic is the theoretical and experimental investigation of chaos synchronization for chaos cryptography in nonlinear electronic circuits, but also in discrete equations where we use to for chaos cryptography. And the fourth one is bio-inspired devices, where we look for self-sustained electronic models for artificial heart pacemakers and artificial neurons. We look for electromechanical models for artificial ventricles, and also for electromechanical models for artificial pancreas, based on mathematical models of the copper, glucose, insulin in our body. And we have not closed our activities on soliton dynamics. We are also working on condensed matter physics, understanding how short topological waves propagate in ferroelectric, superconducting, and biological systems. We have even extended our work on soliton to blood waves, and sun ions in geysers. Well, that was a general information on how nonlinear physics was introduced in Cameroon and how we are working, the topics on which people are working in Cameroon now. As I indicated, a shift came in 1995 when I had the opportunity to be invited to ICTP for conferences and for the association program. And when I arrived there, I was really interested by chaos. And after that, a large part of my research activity was concentrated on chaos. And that is why I would like to present to you why I was interested by that. Because chaos is omnipresent, is present in all scientific fields that I will present to you in this part of the presentations. But first, I will first give some information on, for those who are not familiar with chaos, give some information on how to quantify chaos and how chaos appears in a system. So how to prove the existence of chaos in a system? There are several quantifiers, but the main efficient is the Lyapunov exponents, which measures how the trajectory diverges when there is a change in the initial conditions. And it can also be calculated from data obtained from the numerical simulations, but also from data obtained from measurement of observations. And when the Lyapunov exponent is positive, we are in the presence of chaos. When it is negative, we are in the presence of a periodic state, or in a state where there is no, the system goes to a fixed point. There is also the situation where the system can show quasi-periodic behavior, where the Lyapunov exponent is equal to 0. But instead of calculating only the maximal Lyapunov exponent, we can also calculate what is called the spectrum of the Lyapunov exponents, from which we can be able to decide whether the system is hyper-chaotic or only chaotic. One can also use a frequency spectrum analysis to show the existence of chaos. When the frequency spectrum spectrum is broad, we are in the presence of chaos, and when it is concentrated on particular frequencies, we are in the presence of a system evolving periodically. Now, looking at a system, at the time evolution of a system, can we predict that chaos will come or the chaos is coming? Yes, there are different methods to predict that. The first one is the intermittent route to chaos, where for a given values of a control parameters, we look at the time evolution of the system, and we see that from time to time, the variations is stochastic, is chaotic, and then move from the chaotic state to a regular state. And when we increase the control parameter, the number of chaotic intervals increases, and finally, the system goes to chaos. The second route to chaos is what is called the period doubling route, or also called the Feigenbaum scenario, for which, when varying the control parameters, we first see that the system is evolving periodically. Then with a period, let us say T, and when we change the parameters, we see that in another interval of the parameters, or the variation of the parameters, the system moves from a system evolving from period T, with a period T, to a system moving with a period 2T, and so on. We move also to period 4T, to period 80, 90, 40, so on, and continually at the end, the chaos will appear in the system as we vary the control parameters. Now, there is also another route to chaos, the real-takers-Newhouse scenario, for which the system moves from the periodic states to a quasi-periodic state, and then move from the quasi-periodic state to the chaotic state when we change the control parameters. And the last scenario is what is called the sudden transition to chaos. By varying the control parameters, we arrive at a point where the system can move from something that is predictable to something presenting chaotic behavior. Can we manipulate chaos? Yes, we are also interested in that, to control chaos and to look for the synchronization of, to look for methods to synchronize two or many chaotic systems for applications. Chaos can be controlled in two ways, mathematically, numerically, or through experiment in two ways. The first one is to control a chaotic state to a periodic state. So we have a system evolving chaotically, and we decide to push the system from the chaotic state to a periodic state. And there is another way of controlling, which is to make the chaotic state come to the system, which is called the anti-control of chaos, where we move from the periodic state to a chaotic state. Indicated, we are also working on methods for the synchronization of chaotic system. If we consider two chaotic systems, the first one is the master, the second one is slave, we can be able to find the coupling parameters for which, despite the fact that the system starting with different initial conditions normally evolves on different trajectories, we are able to obtain a appropriate parameter for which we can obtain what is called a complete synchronization, where the state of the slaves is really equal to that of the masters. We can also obtain what is called a generalized synchronization, where the state of the slave is a function of that of the masters. And delay synchronization can also be obtained. Anticipated synchronization can also be obtained, but we can also obtain what is called phase synchronization, where the system, the phases are synchronized, but the amplitudes are not synchronized. Now, our interest on studying chaos came from the fact that going through the literature, we found that chaos can be found almost everywhere, starting from the three-body problem. The three-body problem consists of the interaction of three bodies through gravitational forces. The example is the sun, the earth, and the moon, assumed to be isolated from the rest of the universe, but also there is the extension to the whole planet system of the solar system, where people are studying how each planet evolves, consider the interaction with other planets and the sun. And the question at the time people were studying that was, is the solar system stable? Meaning that are the trajectories of the planets stable? Or is it possible that one day one of the planets will hit another planet, or one of the planets will fly out of the solar system? This is an old question that was put in the 19th century, and Poincaré was the first to demonstrate that each body in the three-body system evolves chaotically, and that was published in an interesting book written in French with the title Méthode nouvelle de la mécanique céleste. And it had been demonstrated recently that the planets of the whole solar system evolve chaotically, so that it is not possible to predict their position for time range of about 60 millions of years. Well, we know that this is difficult to verify considering the large range of time. I put here one reference on which more information can be obtained. Well, after that, the first demonstration of chaos in electronic system was given in 1961 when a PhD student in Japan was working on electronic circuits using analog electronic components. During his experiment, he found that the output of the system was random and showed disordered behaviors. And this was put aside by his supervisors because people were not thinking that the electronic system could give such type of behavior. And so the work was done in 1961 and was published only in 1970. Now, another model in which chaos was presented the first time is in meteorology in 1961 also, where Lawrence and two women collaborators at MIT in the USA, they were analyzing meteorological spatial-temporal equations, and they simplified the partial differential equations to a set of 12 coupled nonlinear differential equations, and later on, they reduced that to a set of 3 coupled nonlinear differential equations. And they conduct numerical simulations and arrive at 2 observations. Thus, there was no order in the data sequences over a large period of time for some values of the coefficients, and that the system is sensitive to initial conditions. And when they obtained the results, there was sort of a debate with colleagues, and some people thought that there was something wrong with the functioning of the computer. But at the end, really, it was found that after verifying many times, they came to the conclusion that the system was evolving erratically. I mean, here it's the random variations of the horizontal and vertical temperature gradients. And that was published in 1963 with the title Deterministic Non-Periodic Flow in the Journal of Atmospheric Science. And it is the first time the chaos was obtained in computer simulation. This reference appears to be the most certain reference in chaos theory, despite the fact that it is parallel to the work conducted by Lawrence and co-workers in Japan. Something similar was found in electronic circuits. Then, after those first discoveries of chaos, people were looking to see whether there is chaos on other systems. In 1976, Robert May solved the logistic equations, which links the density of biological population at a given generation to that of the next generations. The equations is written here, where X is the density, I is represent the generations, and R here is represent a coefficient which is proportional to the birth rate. And by solving these simple equations, it was people arrived at the conclusion that for R greater than 3.57, the response of the system is very chaotically. I'm presenting here also some figures in which we show how the system evolves, consider the interval of in which the parameter R is chosen. So for R greater than 3.77 to 4, the system, the density of the population varies chaotically, as it can be seen here. This was proven experimentally later, and some references are indicated here, where we see that it was demonstrated that the population aperiodic behaviors can be found in populations that were published in Journal of Animal Ecology in 1997, and also there is an experimental demonstration of chaos in microbial food web published in 2005 in Nature. And so from there, people continues to look whether chaos can be found in other systems, in other fields. And here I'm presenting one reference which summarized in 2013 chaos in biological system, where there is a series of contributions demonstrating from models and experiment the presence of chaos in different subfields of biology. I'm also presenting next another book published in 1993 in which one can find information on experimental observation and theoretical interpretation of chaos in chemical and biochemical systems. One of the most interesting is the Belousov-Zhabotinsky reaction, and they can also be found on surface reaction, electrochemical reaction, and enzymes reactions. Chaos is also found in economics and finance. Here I also present a book published in 2009, where it is demonstrated that what is seen as random data in market movement are in fact the signature of chaos in some cases. And nonlinear mathematical models have been developed to really show that the coupling between the price index, the bank index, and so on, investment demands can vary in a chaotic manner. Chaos is found in social science, as it is presented here in the book published in 1997, where it is demonstrated that it is explained that chaos is present also in political sciences, in sociology, in cooperation between individuals, cultural conflicts, language competition, and also education performances. Chaos is also inside our body. it was demonstrated by Glass et al. That cardiac arrhythmias are chaotic. This was demonstrated experimentally through in vivo experiment and data obtained from a chicken heart by stimulating the chicken heart with electric electrodes. They arrive at the end to show that the arrhythmias are chaotic. It was also demonstrated that normal and electroencephalograms are chaotic, and that in the state where the epilepsy arrives, this state is characterized by the presence of order with rhythmic electroencephalogram patterns. The information can be obtained from the references I indicate here. Yes, I indicated the mathematical models to demonstrate what is happening in the case of the electroencephalograms. There are mathematical models demonstrating that it is possible to forecast the apparition of the epilepsy, as you can see in the publication in 1998. These results are sometimes contested by other scientists, but we think that it might be something very, very real, since the experiments have already shown that. What about chaos applications? Well, there are many chaos applications, and the first one is the one you obtain from the synchronization of two chaotic systems. And because of that, it was demonstrated that chaos can serve as for chaos cryptography to mask text messages, image, audio, and audio-video messages with high security because of the large size of the keys, which are the initial conditions. As we indicated, the chaotic system is sensitive to the initial conditions. So the initial conditions I use for my simulations is they are different. If they are different to the one you use to conduct your simulation, we will obtain different trajectories. So the initial conditions are considered also as the part of the keys. The parameters of the chaotic equations of the chaotic system, and what is interesting is that although some information have been obtained, some demonstrations have shown that using chaos, one can be able to get into the code to get the information. What is interesting is that the chaos cryptography can be associated with the classical cryptography methods. Well, I'm presenting here an example of text encryption message that we obtained recently, where you have a message written there. I received my master's degree in telecommunication from the National Institute of Science and Technology. They were done by one of my PhD students from Chad. He defended his thesis last year. And we were looking for how to encrypt text messages using chaos. So at the end, he was able to do that. And the same message is in B. And that is the message that will be sent to the receiver. And we can send him the code to come back to the original message. The second figure is the one really which is used most of the time for chaos cryptography for images, where we show the original messages at the first column and the encrypted images in the second column that are transmitted to the communication channels. And at the other side, one can be able to obtain the original message if one has the code, if one has the keys of the chaotic system. I will not insist on the scheme for chaos cryptography, but what is important to know that at the emission, the message we want to encrypt is used with the first chaotic signals. It's mixed. Let us say it's mixed with the first chaotic signal and sent into the transmission channel. And at the reception, one uses another chaotic signal, which is synchronized to the first one to decrypt the message. Well, Cameroonian specialists on chaos are working on theoretical and experimental methods for chaos cryptography using different channels of transmissions. A second application on which we are working is the chaotic mixers and sieve. It has been demonstrated that using chaos in mixers and sieve, we can reduce the operation time at about 90% and reduce the electric energy consumption at about 92%. And in our group, we are fabricating new mixers or new seeds, or we are using the mixers already in the market. We modify the electric circuits to improve their efficiency. Now for chaos, application of chaos in human body. In the literature, one can find that it is possible to control the arrhythmias by administering using electrical stimuli to convert the arrhythmia to from irregular state to periodic beating of the heart. One can also, as we indicated, epilepsy is after some studies, some experimental study, it was demonstrated that epilepsy happens when there is a sort of order in the encephalogram. So if one is able to anti-control the chaos in the brain, that will give a way to a sort of therapy for the epilepsy. And it has also been demonstrated using rats in laboratory. That was published in 1994 by Schiff and his collaborators. Yes, I already indicated this. Now, I move to the third part of the present, the third and last part, which is also very important in our research group, bi-inspired electronic oscillators. What are bi-inspired electronic biological oscillators? Biological oscillators are a set of self-sustained oscillators inside our body due to internal regulation, for instance, inhibitory feedback or delay, and they present some special features such as personal behavior, relaxation oscillations, bursting oscillations, and sometimes chaotic dynamics without external excitation. And as indicated, they are present in our body, the cardiac rhythms, which is commanded by pacemaker cells, which are self-sustained oscillators, the breathing oscillations, the neuronal firing signals, the vasomotion, which consists of a sort of internal oscillations in the blood vessel to facilitate the blood flow, the menstrual cycle, the circadian regulation, and etc. So this system can even lead to waves when we couple several units, and that is the case in the vibration of the heart cavities, where the signals comes from the principal heart pacemakers and move all over the ventricle and auricles to contact our heart. And that can be used also for millipede motion or the coordination for neural activities. Now, why are we interested in making biological oscillators? The first interest for us is to develop new methods to predict the behavior of biological oscillators under some special considerations, which can be seen biologically, but may be different to difficult to examine experimentally, and we can with the artificial model we can be able to analyze that, and for instance, some example of diseases, we can be able to analyze that before people doing experiment in biology can go into the laboratory to look to continue the experiment. We are also looking for bio-inspired artificial organs, the artificial pacemakers, as we all know, the electronic part of the artificial heart, the artificial neurons, the artificial muscle, and so on. Or we look for new electronic circuits to power some devices, such as actuators for special technological purposes. Or also, it is not mentioned here, a sort of hybrid biological system where we replace part of the biological structures by artificial biological oscillators. And it has also been demonstrated in the literature experimentally that that can be possible, and natural biological oscillator will work without any problem, interacting with the artificial biological oscillators. So how to do that? Well, the first step is to look for the mathematical differential equations whose solution presents shapes that are similar to the one presented by the experimentally by the biological oscillators. After having that, we can build analog electronic circuits or electronic circuit with discrete component, or also use microcontroller to produce the special behaviors that are found experimentally to be delivered by the biological oscillators. I'm presenting here the case of the heart pacemakers, on which we are also working. I'm presenting, you have here the figure of the heart, where you see the first, the main pacemaker of the heart, which is called the sinoatrial node, followed by the second heart pacemaker, which is the atrioventricular node, and then the electric signal flows from those nodes over the auricles and over the ventricles. So the question is, are we able to use the mathematical model that we indicate we obtain to build electronic component, to build electronic circuits which behaves as the natural biological heart pacemaker? We did that, or we are doing that in our group. I'm presenting here two models. The first one is the one using the discrete electronic component, and the second one is the one using an analog electronic component. And doing that, we were able to obtain experimentally the type of signal you find here, which is close to what we observe from experimental measurements of the signal delivered by heart pacemakers, and the frequency, even the frequency can be modified if we modify some components of the electronic circuits. Well, we can also use microcontrollers, simulators to do that. And one of the examples that we conducted in the lab is that of the neurons, how to produce an artificial neuron using the microcontrollers. We did that with this equation we described, is a simplification of the Hawking-Huxley equation for the cells, and constructing this into a microcontroller, we'll be able to generate signals that are sometimes found delivered by some cells in our body. And this is particularly interesting because a work on which we are now is to see whether we can construct a sort of neuronal cortex using a microcontroller, meaning that we put inside the microcontroller a set of artificial neurons, and then to see how that set of artificial neurons will behave, whether it will be able to reflect some of the neuronal cortex that we have in our body. And we are thinking that by doing that, that can be used for some neuronal diseases, such as tetraplegia, blindness, deafness, etc. But we are still on the doing that without conducting the experimenting on animals and so on. Well, for bioinspiration, we are also working on the bioinspire pump from the electronic for the heart natural pump. So you see here two models. The first one is a monoventricular cavity, and the second one is what is called the biventricular models, representing, for instance, the two ventricles of our heart. If the ventricles are suffering, one can think of replacing that by an artificial bicavity ventricle, as you can see here. We have in red, it is a sort of sac in which we assume that there is blood inside, and using electronic and electromechanical knowledge, we were able to demonstrate that the system can vibrate as the ventricles. The last project on which we are working is to understand the physics and mechanics of bird flight, and then to design electromechanical toys imitating the different birds' flight modes. We are not the first to do that. There are many research groups all around the world doing that. But we think that with our expertise in nonlinear dynamics, we think we will be able to obtain something like that. Why are we interested by that? But the first thing is that we want to fabricate some toys which can be used by children to play. But as you know, today, the wars in the world are dominated by drones. And in my thinking, during the next 10 years, war will be done using artificial birds, artificial fish, etc. So I'm thinking on that, but I think this will happen. And they can be used for wars, they can also be to spies or for other purposes. Well, as indicated, I have not insisted on research results from the Cameroonian team. Some indication have been given, but as I presented at the beginning of the presentations, the number of contributions from the Cameroon people working on nonlinear dynamics is very huge. And because of that, we are preparing a very important scientific event in Cameroon in 2026, where we expect to come out with the presentation of most of the results so far obtained since the introduction of nonlinear physics or nonlinear dynamics in Cameroon. Well, I will stop there and say thank you very much. I hope I was able to give you something that is interesting for you. Thank you very much.
Thank you very much, Professor Woafo, for this very inspiring and impressive presentation. So many things that can come out of CAO in some sense. So very good. So we have already, in the audience, a few questions. And so I still invite you and everyone to write down in the Q&A section box down there. Maybe in the meantime, if you don't mind, maybe to close your presentation like this, we can really see you in a better way. That
Yes.
might be easier. Voilà. And on the top right. Yes, super. So
Okay,
I
thank
will
you.
start by, actually, we still have my colleague just before he leaves. Alan, do you have to leave soon? So do you want to ask your question live? Because I think it was fascinating. And we had some kind of connection, but then maybe I let you speak
Okay.
first.
Sure, I may not be able to stay for the answer, but I'm curious about the quantum chaotic domain, where we're used to taking an action, a Hamiltonian action, and summing the appropriate function over all pathways for a quantum, the evolution of a quantum system. Now, if I've got that right, that's what Feynman has told us. But if those pathways become chaotic as you consider all possibilities, how do you think about that sort of a summation? How can we even perform it, or even just plot the strategy for calculating the action? And how would quantum computing help out, or is that even relevant here?
Okay, should I reply to the comment, the question?
Please.
Please.
Yes, okay. Thank you very much. For chaos, classical chaos, presently there is what we call the heredity in the physical, in the biological, and so on system, in which we consider that the present state depends on all the states the system has or had before the present state. And this is introduced in the system by an integral. It is introduced in the system by an integral, and the integral will modify what we call the bifurcation diagrams of the system, modifying the parameters leading to different dynamical behaviors. Now, for the quantum system, we started doing some calculation on that some years ago, looking for how the entanglement can be modified by the nonlinear dynamics. I think maybe at the end of the presentation, I will send you what were some papers that we published on that. Thank you.
Okay, I do have to run, and I want to thank you for the presentation. And I see that the number of participants is very high for this session. So, thank you again.
Thank you, sir.
Yeah, thank you, Alan, for your question. So indeed, and maybe even if we want to summarize, looking at the relationship between the quantum mechanics and this quantum chaos, so how would you describe it just in one or two sentences, quantum mechanics in general?
I would like to say that for now, as indicated, we have not contributed a lot on quantum chaos. I prefer not really to go for that. I prefer to stop there, and I will come back to that later. Thank you.
Very good. So, but that might be an interesting, PhD studies in some sense, if we think in
Yes,
terms
thank
of
you. Yeah.
what happens with this revolution, with those quantum computing and all those things are really important. So, so very good. So, so let me read maybe the first question from Gaëtan Fausto-Coulet, who was asking already some time ago. So if you can please elaborate on the concept of anti-control and its applications.
Okay, thank you very much. The anti-control of chaos is a way to push the system, a system from a regular state, a periodic state, for instance. So you have a system evolving in the periodic states, and want the system to behave chaotically. You have to push the system from the from the periodic state to the chaotic state. That is what is called the anti-control of chaos, which is different to the control of chaos, which means to move the system from the chaotic state to the periodic states.
Okay, very good answer. But does it depend also on the initial conditions, or depending
Yes,
on how
it depends on on the applications, as I indicated before. The example I took was that of the epilepsy. When the case of the epilepsy, where it had been demonstrated that in case of epilepsy, some experimental information indicates that the epilepsy in our brain is characterized by the fact that the information the data evolves periodically, something like that. The electric signals evolve periodically. And in that case, we face the epilepsy. Now, to move from the epilepsy state to the normal functioning of the brain, we need to make a sort of anti-control of chaos, meaning we push the system from the regular behavior to the chaotic state, which happens to be the normal behavior of the brain.
Excellent. And could this be somehow used with now this AI and capacity as well, with having all those imaging and maybe preventing that in some sense in some of the hospital, knowing that chaotic?
Can you go back to the question? I did not get you well.
Sorry?
And the question is, can you repeat the question, please?
No, this is just to follow up and understand if potentially with the case of the epilepsy, it could be as well using some different AI tool, artificial intelligence tools.
Yes, maybe.
A good combination. Okay. Voilà. Okay,
yes,
perfect.
Yes, really. Mm-hmm.
So indeed, now we will have the question for Munya. So Munya is raising her hand. And everyone can also raise hand, huh? Be aware.
Yeah, thank you, Christine. Thank you so much, Professor, for this nice talk. You have actually shown that chaos appears like in so many different areas, like from populations to ecosystems to electronics. So do you like see underlying universal principles of chaos that could guide both natural and engineering systems? There is like
please,
any.
Can you repeat the question? I have a problem.
I mean,
with
you
your
have like
connection.
Yes, Professor. So you have like shown that chaos like appears in many different areas. So I'm not sure if like there is any underlying universal principles of chaos that could guide all those fields.
The omnipresence of chaos.
Yes.
Yes, as I indicated, it happens that really chaos can be found everywhere. If I got you well, it can be found in all scientific fields, and people are working to see how a sort of generalized theory can be developed to fix all those information. That's what I can say now. Yes.
So I do have another question, if you allow me, Christian.
Please.
Okay, so yeah, given like your experience, like in advancing physics in Cameroon and in Africa in general, so which like areas of African development, like healthcare, renewable energy, or infrastructure, could benefit like from this from the application of chaos theory or bio-inspired engineering?
Which topic? Well, I prefer to not to insist only on the chaos, which is only one of the striking information that people obtain when analyzing nonlinear phenomena. Well, in the field of energy, we were talking of the energy harvesting. we're talking of energy harvesting using nonlinear system. And in our group, we have demonstrated that by using simple system in which we introduce nonlinear component, it is possible to increase the energy, the power that is harvested using the simple system. That is, but this is something that is limited to the laboratory. We don't know how that will be in the field, that will work. But in the lab, we succeeded in increasing the energy, the power generated by a system which initially was working linearly by introducing nonlinear component. Now, other scientists are doing the same, do the same in the world. That is for the energy. Now, I was talking of therapy, and I indicated that the bio-inspirations is something very interesting for all the world and for Africans. If we really work on bio-inspiration using material sciences, using other type of sciences, we will be able to construct devices which are very interesting for the development. I talk of the chaos therapy, but I also talk of artificial organs, artificial pacemakers. You know that to have an artificial pacemaker now, we have to buy it. I mean, us in Cameroon, we need to buy it from abroad. But people in Cameroon are trying to build some devices which can help in that way. But we are still, I insist on the fact that we are still in the laboratory investigations. And one of the difficulties that we have is the interaction between people working in physics, doing that, and people working in the field of medicine. It is really difficult for us to do that. The last one is what I was indicating as for defense. What I will ask Africans now is that they need to be highly engaged in bio-inspiration. I'm telling you, in 10 years, you will find that if a country wants to attack other countries, it will send a sort of a large ensemble of artificial flies, artificial birds, and we found that the country is all over the country. We found artificial insects moving in the country for spying or even to harm the population. If there is no regulations, as it is the case for biological arms, if we do not arrive at that point, I'm indicating clearly that in 10 years' time, we will be submerged by artificial birds, artificial insects, and so on. And so Africa needs to prepare themselves on that field also. Thank you.
Thanks.
Thank you, Professor.
Thanks for this question as well. So we have much more question, if you don't mind, to answer to Loeni Sotamgwa, who is asking about your presentation. If you look at the slide 25, so in your presentation, 25, it was series.
Let me go on that. 25.
HR oscillator.
Yes, I will get on that. Yes, 25 is on the generation of signal similar to that of the neurons.
Exactly.
Yes.
So on the bottom right figure, so there is a neuronal behavior. So in response to a stimulus, a series of spikes are generated. And it's only a single spike, as on the other figure. So it means that, voilà, so which real biological situation can explain that result? How do you explain?
Really difficult to say, because our neuronal system is very complex. Really, when you engage yourself in studying the dynamics of the neuronal system, you find that depending on the type of the excitation you have, you put on your system, you will find different reactions or different electric signals that will be generated. So I cannot really indicate that in this case, this is for this correspond to this situation. But as far as no, we try to look for how the neurons act on our muscles for us to move something. It was indicated that this happened when the neurons send a sort of high frequency signals to the muscles before the muscles start to move. So we try to use some to couple this to an electromechanical system in order to see how the mechanical system will behave. But till now, we have not been able to come to the conclusion that this is really what the response that we obtain from the electromechanical system is really how the muscle reacts when it receives the command from the motor neurons. But the indication in the literature is that the motor neurons, when the motor neurons want our muscle, want us to conduct a movement, the motor neuron sends a sort of a package of high frequency electric signals to the muscles.
Okay, very good. So still like some privilege as well from the nature to hide some of those secrets from us as well.
Oh, okay.
Yeah. So then another question from Jimmy Hervé Talimembe, who is asking, so if somehow, so those bio-inspiring prototype like bird or fishes only used for war, is there any positive application? How would you foresee positive application for that too?
Okay, the positive spying is not a bad application. Spying is not a bad application. If you want to protect yourself, you need to spy. So you can use your birds, your artificial birds to spy. You can use your artificial fish for spying. So that is a first application. But you can a first positive application. But you can also use your birds, your artificial birds. You insert on your artificial birds some cameras to look all over the city to see how the traffic is working. Similar as the drones are doing now. Instead of using drone, which is a drone which is huge, you can at the end use a large number of birds to do the same activities. It's okay.
Very good. Very good. So then another question from Faisal Bazi, also one of our students from the SPS. So looking at two questions actually that he has. So is the nonlinearity in nature a fundamental aspect or an emergent one? So that was also comparing because as you know, so the linear is an important principle in quantum mechanics. So where does the nonlinearity come from fundamentally? What would you say? Fundamental. Can we explain this with quark and quark standard model?
When the nonlinearity comes, if we consider only what we call the oscillator system in quantum mechanics. In quantum mechanics, we have linear oscillators. I'm now in the fundamental studies. You have linear oscillators, but you also have nonlinear oscillators. We also have particles moving inside a box. When you have a box in which a particle is moving, you are really in a highly nonlinear system, because if you consider the potential in which the particle is moving, it is nonlinear. It is something which is nonlinear because of the discontinuity. So that is where we can have a nonlinear component in quantum mechanics.
Okay. And then his second question also, so if he didn't misunderstood you, so as well, so you worked for your PhD on the effect of discreteness on the property of nonlinear waves, so like the soliton. So could so this discreteness be the source of this nonlinearity that is by
No,
taking the continuity limits, so the
no,
underlying of nature?
no. The discreteness is not the source of the non-linearity. When we consider an atomic lattices or atomic lattices, we know that the atoms are interacting through atomic potentials or atomic forces. And the atomic forces are by essence nonlinear. We have an atomic force which is a sort of an exponential function. It depends on the system on which you are working. So you have the atomic force between two particles, which is a sort of exponential functions of the distance between the two particles. This is already the non-linearities. So it is not what I was looking for. We consider at the time that the system is nonlinear by essence, but the materials is by essence not continuous. It is not continuous. Any material that we have with us, it is constituted of particles. It can be constituted by atoms, by molecules, etc. And then inside that material, you have a soliton which is propagating. If your solitons is very short, if your solitons is very short, it interacts with the particles in the system. So you have to take into account that the soliton being very short, which is also considered as a particle, we interact with the atomic lattices, and we need to take into account that interaction to see how the soliton will evolve. And at the end, we found that because of the discreteness of the lattice of the system, the soliton was moving as a particle moving inside a sign potential. And this is understandable because if you have you have two atoms and you have a waves propagating between the two atoms, they will see the distance between the two atoms as a potential. We will see this as a potential. So we demonstrated, we calculated the characteristics of the potentials and so on.
Okay, very good. And also related to this soliton, just I jumped to the question of so Christian, so Sadan, asking, so since the power of the soliton is directly related to its amplitude, so how can we alter as well the balance between this nonlinear and the dispersive effect that keeps them stable?
Well, the soliton is a special object of nonlinear science. And the soliton appears when there is really a balance between the nonlinearity and the dispersion. If the dispersion is dominant, your signal, your input will disperse. It will disperse and gives rise to linear waves. If the nonlinearity is dominant, your system will break down. So the solitons appears when there is a sort of compensation between the nonlinearity and the dispersion, and that we have the soliton propagating in the medium.
Okay, yeah, brilliant explanation. So then we have like an interesting anonymous, so asking as well, so for this cryptallography, so using the cow, is it like hackable or unhackable? And so is it to the same initial condition do not give the same output? So the cryptallography part and the cow.
Crystallography?
Yeah,
Cryptography or crystallography?
Cryptography, sorry.
Okay, please. Okay. So what is the remark?
So is the cryptography using the KO unhackable? Can you hack this cryptography, sorry, thanks to this theory? Is there a way? This is the question indeed in terms of between the the aspect of the quantum and the chaos. So is it some solution as well potentially for this cryptography using and explaining? I mean, this is what you describe in some sense. So maybe if you summarize how it does.
How the cryptography works? Yes, I can explain this simply. As the keys, as I indicated for, no, let us start with the chaotic system. A chaotic system is sensible to initial conditions. So if you have some, if for a simple digital system, I put 1 and you put 0.5, and we are in the system, or we are in a chaotic system, and that we look at the time variations of our data. We found that our data are evolving in different arbitrary, meaning that the values of the data per time are different because of the initial conditions that we use were different. Okay, because of that, if two people consider two different conditions, it means that they are not having the same chaotic trajectory. Now, to be able to synchronize, we need to use it for chaos cryptography. We need to have at the emission a chaotic system, at the reception another chaotic system, and we set into motion the two chaotic systems with the same keys, meaning that with the same, for instance, with the same initial conditions. And we have to know that. So I use, if I want to encrypt the message and send you the message so that you will get the message, I will give you the keys, all the parameters for the keys, meaning I will give you the initial conditions of the system. I will give you the parameters of the system, and then you set your system into evolutions. It can be an electronic circuit, an electronic nonlinear electronic circuit. It can be an optoelectronic circuit, as I indicated before. And so you send the system into, you put your system on, and we look for the parameters. Even if you use different conditions, we will look for a coupling parameter between the emitting chaotic system and the chaotic system at the reception. We look for a coefficient. We will couple the two systems so that they will evolve in the same trajectory at the end. Now, at the emission, I take the message. I mix it. I will not go into the detail of what, to explain what we mean by mix, because mix means many things where we are working on that. I mix the original message with the chaotic message. I send that to the transmission channels. It means that when you are in the transmission channels and you want to obtain someone is there and try to get the message, he will receive something that is not readable. Now the message will arrive at the reception, and because at the reception, your system is already synchronized to the one I use to mask the message. You just have to make a simple subtraction, but this is easy to say that. You just have to make a simple subtraction between the message you receive and the message you have at your position, which is the chaotic message. If you make the difference between the two, you will obtain the original message I sent to you. But again, I say you subtract, I say you mix. You have to be with people working on that to know what we mean by mix, what we mean by subtract. It is something very complicated. Not so complicated, but when you are inside, you can understand really how it works.
It is good, and we need indeed those quantum computer potentially for the hacking aspect or unhacking. So, and I just want to also have, so we have two questions.
We'll work on that.
Indeed. So we'll have so from Professor Malzi. So
yes, I'm there for that.
Malik Maza. So sorry. So Professor Maza, wonderful to have you with us. So can you unmute?
Hello, Ali. Hello, Malik.
Hi.
Happy to have you. Hi, Malik. I'm really happy to have you. Thank you.
So much. Thank you, Prof, for this outstandingly enlightening, wonderful indeed speech and talk.
Thank you, Malik.
Whenever we speak about cow, it is related and correlated to energy dissipation. Correct me if I'm
Yes.
wrong. This is really a challenge when it comes to ultra miniaturized microprocessors, which are really the backbone of artificial intelligence, machine learning, supercomputers, and so on. How can we, according to you, please, minimize these chaotic components in this sub-nano microelectronics, future microelectronics?
Oh, really interesting. Well, as you indicated, the chaos can appear because of the dissipation, and the dissipation might be due to the temperature levels.
Correct.
So maybe I don't know. Maybe by cooling. I don't really know what can be done. But I think if we are able to really characterize the system, we are able to really characterize the system, to characterize the chaotic dynamics of the system. We can use one of the methods I indicated before to control the chaos. We can do that to control the chaos. I don't know really how to do that, but I think having the system with me at hand, having the equation describing the system and how the system works, I think we can be able to come out with something really interesting. We can help to reduce or to control the system so that it moves from the chaotic state to the regular dynamics that we want to have.
Thank you, Prof. I would be grateful to you if you could accept our invitation to visit us for 2 weeks in South Africa. We'll be delighted to invite you and to cover everything.
Yes, I would like to apologize, Malik, for last time you were asking me to send you some information on what we are doing on semiconductor lasers and optoelectronic oscillators. I really apologize because it was the time for me to send that to you. I forgot. So I will do that after the presentation. Thank you very much.
Thank you so much.
Okay.
That's a great opportunity. And then maybe your last question, indeed, from Somona Mosan. So, and you can connect later on, maybe even if you want to ask live or listen to the answer. So to what extent, so this therapy can be successful in remediation of disease such as the multiple sclerosis?
Please, can you repeat the question?
So if you look in the question and answer, so to what extent, so the theory can be successful in the remediation, so I guess to be able to fight the disease of the case, for instance, of this multiple sclerosis?
I'm not sure that I really have the response for that.
It's a specific
maybe I will have to look on that. I don't really have an answer for that, but it is an interesting question that is for applications of chaos. We have to look on that.
Interesting question. So indeed,
yes, really. Mm-hmm.
Yeah, very good question.
I think, Christine, there is also another question in the chat coming from Tisama.
So please, can you read it because I didn't go.
Yeah, is asking how did you secure such a successful program given the challenges, brain drain, resources, etc.?
Please let me read. Please repeat the question again, please.
So the question is like, how did you secure such a successful program given the challenges related to brain drain, resources, infrastructures, and so on?
Well, we were really lucky for our. You mean the brain drain? People moving from Africa to other countries?
Yeah.
You mean that?
Yeah, and
Okay.
also other challenges, not only brain drain.
Yes.
Also, like securing funding, like how can you manage to have that successful program beside all those
Yes.
challenges that we do have in Africa?
Yes, we were lucky in Cameroon, as indicated, because ICTP, the International Center for Theoretical Physics in Italy, really helped us to organize our activities in Cameroon without the necessity to travel, to go and stay abroad, because we had the opportunity to go there to work for 3 months every 2 years. And it was really sufficient for us to get information, to get information. Now for the students that we have been able to supervise so that they obtain their PhD thesis, I think at least 75% are working in Africa. 75% are working in university or research institute in Africa, and some of them are working on abroad. Universities, I think about 10%. Some are abroad and no more working with research. Now, how to if we want to combat the brain drain, it is something that needs first the engagement of the political leaders from Africa. The solution should first come from Africa, not from those abroad. But if those who are abroad really wants to help to solve that problem. Some years ago, I had a presentation during a meeting of the European Physical Society, where I was indicating that one of things that would be very interesting for collaboration between partners from Europe to Africa is to construct in Africa research centers doing both theoretical and experimental physics. I was talking on physics, and so that some programs, research programs that are developed in Europe or in America, we can work together. We can really work together. But I think that today we are going to what I was proposing, because last time I was in Germany, and one of the foundation which invited me there was asking how a thing like that can be organized. And so that is what I think. But the problem is to be solved by Africans. The problem is that African leaders should clearly indicate what they need, what they want. Do they need scientists? Do they need people with some expertise? They need to define that. If they cannot define that, if they clearly define that, they will put the price. They will put the price, and by putting the price, people will stay in Africa. Putting the price means you have to pay good salaries. People paying the price means that scientists, for instance, should be happy to see that what they are doing is solving some problems in Africa. It is not the problem of the scientists alone. It is a problem that political leaders should take at hand.
Exactly.
Not Europeans. Not Europeans. The Europeans can help. Europeans can help. Americans can help. But if they think that by having some people coming to their environment, to their laboratory, they will work better. They will not work for us, because we need to organize ourselves. Thank you.
Yeah, very good.
That's true. Yeah, we need also to promote inter-African research collaboration and work
yes,
together.
Really.
Yeah,
we need that. We need that.
that's true.
Exactly.
We need that to define clearly what we need, to define some developmental goals in Africa where science is necessary to solve the problems that we have. If we can define that clearly, and I remember last time we were talking about the synchrotron. Yeah, the synchrotron lies
Yeah.
with Professor in the United States. Let me, I forgot the name. Sikazi. Sikazi in US. Yes, we were talking about constructing something like that in Africa. But we need the engagement of political leaders. It is not a problem that we work on that, but if the political leaders will not accept to fund, that is important for Africa. Maybe we will finally go all in politics to see where we can find a solution.
Exactly. Politics, this is multidiscipline in that sense. And we had indeed the synchrotron, some presentation on the Physics Matter platform, but as well with UNESCO and the IUPAP, as well some very presentation. And indeed, to develop potentially as well a niche, this is what you have done, that you have been capable to do in the case of this quantum, this scout, but then as well a hub. Like this is something that could be also in the case of Cameroon, be like in Yaoundé as well, because it has to be a physical hub at the same time than maybe a virtual one. So it's, but behind as well the societal challenge with the society of Africa. So I think this is like an excellent step towards solving all of that. Excellent. Okay. So I think that indeed, so time is turning, flying even, and so with we will thanks again. So Professor Woafo, excellent presentation that simulates so many questions, and I think we'll stay tuned. If possible, we'll put as well your presentation in our webpage so that people can follow everything as well. With the language, sometimes it helps, even if we are francophone for some of us. And then we can so see the voilà. So you have also in the chat many people that recognize you, and I can share with you. So all of that later on. But I think you are so well known that so people are very grateful that you could speak up like this and record so this message that you are passing to the world. So how Africa could lead in many aspects as well. And with the CAO, so that's even more impressive. So then I will finish with indeed so mentioning so the next presentation of October 30th of October at the end of the month, where we will discuss and go on our trip so around so Africa. The journey will be in Ghana, and indeed with UNESCO. So there are a lot of work with this quantum aspect, so that will be an interesting one, but especially to empower the youngs and this young's innovation for Africa future. And this will be so Rich Michael Wellington who will present so live from Ghana on the 30th of October at 4 p.m. Paris time. So in Cameroon, indeed, that would be 3 p.m. or at 10 if you are in Washington or in America. And everywhere on the planet, you can always watch it back from our series with the webpage that I shared earlier and on the YouTube channel. So thank you very much to everyone to have listened. And indeed, we had a very nice audience. And so we'll tell you, see you soon. So maybe next month. And really encourage you to keep science on the center of